This is the intro video for Lab 3 of the Apsc 1299 labs, and this week we're looking at digital input-output. Now, if you've watched that other video about how to work with the breadboard, then a lot of what you're going to read to begin with here is just going to be a refresher. So where you get to do some new stuff is down here where they ask you to start building some circuits. So I'm going to scroll down just a little more. Here in the table at the bottom of the page, they list all the circuits they want you to make. And all of these are going to be several resistors in series with one or more LEDs. So you're going to build each of these circuits and take some measurements. So coming back up here again, you will remember that strips of 5 holes on the breadboard are connected together electrically. However, this bank at the top of the breadboard is not electrically connected to the bank at the bottom. So they suggest that you hook up your resistors across the gap, just because that is a nice way to isolate the 2 legs of the resistors. And then you can make a lot of different circuits very simply just by moving some short little jump wires in here as you need to. You're going to be building all of the circuits in the table down below, and for each one of them, you want to note the brightness of your LED after you power things up, and you're also going to take some measurements. You're going to use your Dmm, a digital multimeter, to measure the voltage across each of the resistors and also across the LED. Then you're also going to get the current through your LED, and this is a little bit tricky because LEDs do not obey Ohm's law because their resistance does not stay constant the way a resistor's does. So in order to get the current through the LED, we're just going to recall that it's hooked up in series with the resistors. And in a series circuit, what goes in must come out. So if we want the current through the LED, what we need is the current coming out of all of the resistors. And the resistors do obey Ohm's law. So you calculate the current coming out of all your resistors. That equals the current going into the LED. And then you use that current in conjunction with the voltage that you measured across the LED to calculate the power being used by the LED. So before I go on to the next part of the lab, I'll just note that if you're feeling a little rusty on reading the color codes on your resistors, there is a color code chart in your lab manual. It's in the notes number 4. So I'll just go there quickly. So here is the resistor color code reading chart. And as I said, this is in your notes number 4. So you look at your resistor and there should be about 4 bands, possibly more. One of them is at one end and the others will be grouped at the other end. So starting at the end where you've got a group of bands, the first band tells you what the value of the first digit in your resistance is. The second band tells you what the second digit of your resistance is, and the third band is called a multiplier. So using this as an example, the first band is red, so you go and look at the chart, and that says that the first digit should be a 2. The second band is green, so you go and look at the chart, and that says the second digit is 5, so 2, 5 are our 2 digits. And then we look for the multiplier, and blue is times 10 to the 6. So that means that this is 2, 5 times 10 to the 6 ohms, or 25 mega ohms. The tolerance is basically an uncertainty for the manufacturer. So if you've got a gold band, that means that according to the manufacturer, this resistor is 25 meg ohms plus or minus 5%. So this is a useful thing to have. You might want to get a color photocopy of it and paste it into your logbook. Also, if you scroll down to the next page, there's a little refresher here on how to calculate the equivalent resistance for resistors that are in series or resistors that are in parallel. And you may need this in order to calculate the equivalent resistance of your circuits for the experiment and therefore be able to calculate the current going through all of your resistors. And while I'm here, let me show you something else that's in your notes number 4. So later on, they've got a schematic of some LEDs that you might see. Now, the negative end of your LED is always going to be the short wire. Some manufacturers will also flatten the plastic of the LED on that side. So I've got a little picture here to show you. So this is a schematic looking straight down on a circular LED. And as you can see, they've flattened one side of it, and that's the negative end of the LED, which also corresponds to the shorter of the 2 legs. Now, unfortunately, not every single manufacturer obeys that convention, so sometimes the only thing you can do is to plug the LED in and see if it lights up. So now, going back to the lab, now we can scroll down to the next part of the experiment. They've got a question here for you to answer, and they do make a note down here at the bottom that you should always write down notes even if things are not working out right. Also, they've got some grief savers here. The last one's probably the most important. If you smell smoke, turn off the power. It probably means you're burning something out. In Part B, you're going to be programming your chip's pins to be inputs or outputs. So if you program a pin to be an output, that means it's going to output either 5 volts or ground, depending on how you program it. If you program your pin to be a digital input, however, that means it's sitting there waiting to detect whether it gets 5 volts or ground. So an input is a sensor, and an output outputs 5 volts or ground. Now, most of the pins on your chip can be programmed to be digital inputs or outputs, and they're grouped into 4 ports, and they're called port A, port B, port C, and port D. Each of those ports consists of 8 of your pins. Now, in order to program the pins of one of these ports to be either inputs or outputs, you use a special function register, which is a byte of memory. And these are labeled tris A, tris B, tris C, and tris D to control the 4 different ports. This box down here explains how you can use these variables to program your pins. So for example, they've got tris D, and they set it to a binary number. So the 0B tells the program that it's about to get a binary number. And each bit in this binary number is going to program one pin to be either an input or an output. So the first bit is set to 0, so that means bit 0 is set to 0, which turns it into an output. And the next bit is also set to 0, so bit 1 is also going to become an output. So the first 4 pins in the port are going to be outputs, and the next 4 are programmed to be inputs. So this one here is set to 1, and so down here, bit number 4 is set to 1. That means that it's going to become an input. So they set all 8 pins at the same time. And by the way, zeros and ones kind of look like O's and I's, which is how I usually remember that it's output or input. So now let's go on to the next bit. So here they're noting that you don't have to set all of the pins in your port at the same time. You can set just one pin. So instead of using tris D, you would instead use tris D bits and then the member operator, which is the period, and then you'd say which pin you want to set to be an input or an output. So RD2 in this case. So if you want to set just one pin to be an input or an output, you can use this tris D bits. Now, if you have set something to be an output, that means you can also set it to be either high or low. So that's what they're demonstrating here. They've used tris D to set all of the pins in the port to be either outputs or inputs. And then they use this port D special function register to attempt to set all your outputs and inputs to be either high or low. It's only going to work in half the cases, however. So if you've set a pin to be an output, then you can use this port D to set the output to be either 5 volts or ground. However, if a pin has been set to be an input, then this port D won't do anything. So this first bit has been set to be an output because they've got a 0 here. So bit 0 is set to be an output, and they've set it to high with this port D. And the next bit, bit 1, was set to be an output, and they set that low. The first 4 bits have been set to be outputs, so they can be set to high or low. The next 4 were set to be inputs, so it has no effect when you use this port D special function register on them. So only the smallest 4 bits actually get set to 5 volts or ground because they're the outputs. And again, just coming down here, it is also possible to set just one pin rather than the whole port to be either high or low once it's been set to be an output. So down here, they're just noting that you can't draw too much current out of your chip or you'll burn it out. So the chips that we're using can only tolerate about 25 milliamps of current being drawn out of them. And an LED all by itself would actually draw too much current. So you always need to put in a buffer resistor as well. So in this part of the experiment, they're asking you to calculate what the minimum resistance of that buffer resistor should be. Remember that you set this pin to be an output and you set it to either high or low, and high is equal to 5 volts. So that means it's going to be 5 volts across both the resistor and the LED. And if you assume an LED is roughly 2 volts, that means that the resistor is going to be roughly 3 volts across here. So using 3 volts and Ohm's law, you can figure out what your minimum resistance here should be in order to have the current be 25 milliamps or less. So now coming down here, they note here that you've been provided with some source code, blinkrd2.c, so you get that off the website, and you're going to create a project with this, and it's going to cause an LED to blink on and off. So you make your project, and you observe the behavior. Remember, when it says observe the behavior, that means write stuff down. So take good notes in your logbook, And once you've got it all working, you're going to open up the simulator and a watch window. And to the watch window, you're going to add your tris-D and your port-D special function registers. You add some breakpoints to your source file, and then you're going to observe how the values of those two special function registers change. And just like last week, you'll get the most out of it if you display them as binary numbers. So in Part C, you're going to add some user control in the form of a push button, such that when you push the button down, the LED turns on. When you let go of the button, the LED turns off. We're going to use pin RD1 as our input, which means we need to configure it as an input. So that's what they've done down here in the box. RD2 is still being set to an output, but RD1 is now being set to an input also. But then we need to write some code that is going to turn the LED on when the button's been pushed and turn it off when it's been released. And that's what they do down here. They say, okay, when pin RD1 is high, set pin RD2 high also. And likewise, if RD1 equals 0, that is the button's not pushed, then set RD2, the LED, to low. So this is nice and clear, but you actually can streamline the code a bit, and that's what they've done down here. So this does exactly the same thing. So if RD1 exists, that is it's high, then set RD2 high. Otherwise, set RD2 low. So exactly the same functionality, but it's a little bit tidier. However, you can even do better than this, and that's what they do down here in the third box. They just say, whatever RD1 is, set RD2 equal to it. So if the button goes high, then you set the LED output also to 5 volts. Next, you're going to be given a file called control RD2, and it's going to take care of turning the LED on and off, but you're going to have to actually wire the push button. Now, the push buttons are not necessarily trivial to understand. Some of them have 4 pins, some of them have 2 pins. So you should grab your multimeter and actually test how the switch works and make sure you understand at what point the pins are connected together electrically. And then down here, they show you how to wire up the circuit that you're going to use in your new project. And I just want to explain how this works. So this is the push button right here, and it's connected to 5 volts on one side. And then on the other side, it's connected to pin RD1 through a buffer resistor, but it's also connected to ground via a different buffer resistor. And why is that? Well, when the button is not pushed, this pin RD1 is connected directly to ground via 2 buffer resistors, but still, it'll go to ground. And that's important because one of the big mistakes that students make is assuming that if I don't connect this to 5 volts, it must be at ground. That's not necessarily true. You can have a voltage floating on your board just due to static electricity. So if you want something to be at ground, you actually do need to connect it to ground. So this will be connected directly to ground when the button's not pushed. When the button is pushed down, then RD1 is going to be connected to 5 volts. Some of the current's going to come down here. Some of it is also going to come down here to ground, but this is 10,000 ohms and this is only 200 ohms. So that's not going to adjust the voltage at RD1 very far downward from 5 volts. So it'll still be enough to trigger the chip. And by the way, the reason why we have 200 ohms here is just because it's easy to misprogram your chip and accidentally set this to be an output instead of an input. And then if you hooked it up directly to 5 volts, you could burn out your chip because you're drawing too much current. So we stick the 200 ohms in there mostly as a fail-safe in case we misprogram the chip. And the 10,000 K is just to make sure that we don't adjust the 5 volts down very much. So that's how your input button is going to work. And the output is just what you had before, a buffer resistor and an LED. And by the way, they also would like you to hook up your LCD for future use. So finally, once you've wired up that entire schematic, you should build and test a project based on this control RD2 program that you've been given. And also use your DMM to check that the voltages at the input are indeed going to 0 or to 5 volts when you push the button down. In Part D, you're going to be exploring in-circuit debugging. So when you read about the simulator for Lab 2, you will have read about this also. It wasn't part of Lab 2, but it was in that same Appendix E. So we're going to be using it this week. So the main difference between in-circuit debugging and the simulator that you used last week is that the simulator you used last week is running on the computer, not on your microchip, which means that if you've got a button hooked up to your chip and you press it down, that simulator can't detect that fact because it's doing its thing on the computer, not on the chip. So with in-circuit debugging, you are actually running a simulator where the microchip is embedded in the application, which means that if you push the button down, it can detect that fact. There are some limitations to in-circuit debugging. The main one is that you can only install up to 3 breakpoints. It also handles the breakpoints a little differently than the simulator you used last week. So do read through this paragraph to make sure you understand what the differences are. So you're going to run the control RD2 program and use in-circuit debugging, and you'll add some breakpoints. And you want to also open up a watch window and watch the port D special function register in binary. And then you'll step through your project with your finger on the button and with your finger off the button and observe what happens to that special function register. They also want you to play around with changing the value of RD2 by hand in the program from 1 to 0 and seeing if it makes a difference to what you see on your breadboard. In Part E, you're going to be adding code to the Control RD2 program in order to display a message on your LCD. So when you push the button down, the LED will light up and the LCD will display a message. And when you let go of the button, the LED will turn off and the LCD will display a different message. Now, one of the things they ask you to think about here is that if you're updating the message on your LCD every single time the while one loop executes, that's really inefficient because that while one loop executes blindingly fast compared to a human being. And especially if you have a clear display command in your code, updating it that fast is going to result in a faded display. It's just changing too often. So down here, they ask you to try to come up with a way in which the LCD display is only going to be updated when the button has changed state. So not all the time, but only when the button changes. You're going to be learning very soon the correct way to do this, but in this week's experiment, we just want you to take a first stab at solving this problem. How can you make it so that the LCD display is only updated when there's a change, not every single time the while one loop executes? In Richmond, the digital multimeters are usually located on your desk, or they will be located on that table up at the front of the room beside the technician's office. You turn them on with this switch here. If you want to measure voltage, you would be on this setting, and you have your 2 connectors hooked in here. If you want to measure the resistance, you turn to that setting, and you will need to move one of your plugs over here. So you always have one connector plugged into the COM terminal, and then the other one will move to whichever other slot is appropriate. Hopefully your connectors will have these alligator clips on the other side. These are useful for plugging into your circuit in the following way. You take a little piece of wire, you hook the alligator connector to that, and that allows you to then probe your circuit in a way that doesn't disturb anything. So again, hook the little piece of wire into the alligator clip, and then you can plug it into your circuit. You could, of course, attach the alligator clips directly to a resistor, for example, but you run the risk of pulling it out or possibly brushing against some other wire and causing a short. To find the Dmm Sensor, you go up to the front of the room, and over in the right-hand corner beside the overhead projector screen, there's this gray cabinet. Now to get into the gray cabinet, there's a latch here, and you lift up on that, and then you can open up the cabinet. And the DMMs are going to be located inside, and the cables you need are located here in the door. Now most of the DMMs in the cabinet are ones that you can use. We've got these older gray ones, those are fine for you. Down here where it's a little hard for you to see, we've also got these yellow ones. These are actually the ones I recommend you use. There's also some yellow ones farther down in the cabinet, but they're probably not the ones you want. So I actually recommend these yellow ones that are on the middle shelf. And as I mentioned, the cables that you need with the alligator clips are just clipped to the inside of the door here. So you can take 2 of those for you. And regardless of whether you're working in Surrey or in Richmond, the DMMs and the cables have to stay in the labs. We need them for other experiments, so you don't get to take them home, sorry.